It's not supposed to be. When we were to the class, Jess said, why are you 20 points off? I had a question that only was 2 points. Or whatever. Yeah. Yeah. I want this to be just it just doesn't make sense. I just spent 3 hours in another lab, and we're using Cadence on 2D servers. Yeah, remember Cadence circuits too?
Yes.
I have to work on that. And since I wrote it 53 7321, I cannot access the module to a simulation. So I just spent 3 hours there.
All right, let's go ahead and get started with lecture 8. And to get started on this one, let's harken back a bit to lecture 7 and do a quick recap of basically three main ideas that we want to make sure we capture because we're going to use them a lot today. So we talked a lot about our model for sampling. And that was del of t minus cap nt. So given this model, sampled signal, and the impulse train to discrete time conversion, impulse train to discrete time, and that gave us the discrete time signal x of n. And we spent a lot of time last time looking at each one of these components and relating them one to another, mainly in the frequency domain. So our salient result from last time was that the sampled signal in continuous time was what? It was a scaled version, 1 over t, of a bunch of shifted spectrums, which we wrote. The continuous time, which was unsampled, shifted. And I think we wrote that as what? Omega minus k omega s. So we were able to relate the sampled signal to the input. Then what about this impulse train to discrete time, that mysterious block? That was simply just a scaling. And so it was a very simple way to relate the spectrum of the discrete signal back to the sampled version. Remember, there's our discrete spectrum, and if we let omega equal capital Omega times t, we ended up with what? XSJ omega. So using this result, we could easily relate this to this. Of course, we can also go backwards. And so I'll do it on another sheet. And we'll do that a little bit today. Given this, you can also go backwards where we end up with this. So we can easily relate XEJ omega, which is the discrete time spectrum, to this. So we can go back and forth. And finally, if you put it all together, what you might really care about is I care about the discrete time spectrum. How does that relate to the input to this entire system? And that was just going back to the continuous spectrum and plugging in our scale factors. We can get what? K 2 pi over t, where t was the sampling period.
How does plugging in omega over t into the j, how does that equal to e to j? Step 2.
How does this?
No, above. How does that relate to the?
How do these two relate?
Yeah.
It's basically this relationship here backwards. And so, given that, you can rearrange it so omega is small omega over t, and you should be able to get to here. And that was our that was a portion of the lecture last time that tied these two together, was this scaling. Okay. So given those relationships, we kind of stopped there and we talked a little bit about the scaling, but we didn't do really an example to kind of unpack this and make the ideas concrete. So that's the very first thing I'd like to do. Say, okay, we've got all this apparatus and machinery, let's apply it to the problem. So let's do an example of a cosine signal. So let's do cosine of 2 pi 2000 t. So we're going to take this signal and kind of march through the spectrum of it at various stages. But first off, let's see. So we've given this, and we're given that t is what? 1 over 6,000. So from this, we can start saying, all right, is there aliasing at least? We can figure that out. So f samp is 1 over cap t, so that's just 6,000 hertz. And what is omega n, the highest frequency? Remember, omega n was the Nyquist rate, which was the highest frequency in the signal spectrum. Just kind of writing it out to remind us the highest frequency, which for us is just going to be 4,000 pi, right? That's radians per second, but we could also look at it as hertz. So maybe we could call it F sub n, Nyquist, 2,000 hertz. I'm doing it both ways because most of the time we're going to be dealing in hertz. So we might as well convert all this stuff and think of it all the way through in terms of hertz and radians per second for this simple problem just to kind of tie it together. So start off, let's ask the simple question. Is omega s greater than 2 omega n? Remember, that was basically the condition for the Nyquist sampling, Shannon sampling theorem to hold. If that was the case, we wouldn't have any aliasing. So that's kind of our first question. Well, omega s is what? Two pi over t. Cap t was 1 over 6,000, so that's 12,000 pi. What was omega n? So one way to look at that is that greater than 8,000 pi, which is just 2 times omega n. And the answer is yes, so there's no aliasing.
Question.
Yes.
Is the value for omega n given in the question?
It's inferred. Good question. What's omega n in this problem? Well, you can kind of tell that there's, if you remember what the Fourier transform is of the cosine, it's just two delta functions, right? And they're both at 4,000 pi, so so that's why omega n is 4,000 pi radians per second. Many times you'll have a spectrum, there'll be one that has been shaped by an anti-aliasing filter, or you have a priori knowledge about what it is. Now the other way to think about this, which is important because that's how we're going to do it in all the practical problems that I've ever seen, is we talk about this in terms of hertz. So is f_samp greater than 2fn? Of course, the answer is the same since we know that it's all off by 2 pi, but let's just go through it. So is 6,000 hertz greater than 2 times, and our frequency was what, 2,000 hertz? So that's 4,000, so yes, there's no aliasing, because 6,000 hertz is the sample frequency, and that's greater than 2 times the highest frequency in the signal. So we're in good shape. So nothing tricky yet. Let's keep this sheet. Let's do this. So what is x of n? So we're taking samples every 6,000 hertz, and we know that's going to be the continuous time version with the index n and sample time cap t, right? So feeding that through, we've got what, 4,000 pi times t times n. Which just a little bit of algebra shows is what, 4,000 pi, 1 over 6,000 n. Thousands cancel, so it's what, 2 pi over 3 cosine. Actually, it's not 2 pi over 3, it is 2 pi over 3, 2 pi over 3n. So there's our discrete time version of the signal. And we're going to get to that, I hope, through our frequency scaling that we've talked about. So we'll see it here, which is basically common sense, and then we're going to apply all our apparatus, and you'll see it's the same answer, which it better be. So with that in mind, let's start off taking the Fourier transform. So if you recall from last time, any cosine omega naught t had a Fourier transform of what? Pi L omega minus omega naught plus pi delta function of omega plus omega naught. And we recalled what? If we're going to sample this signal, we have our favorite sampling formula here. XC, and it's what? J omega minus K. J omega. And we'll write that as K omega S all over K. So we're going to apply this to get all the shifted versions of that, and then to get XEJ omega, which is what we're kind of after, we're just going to let XSJ omega, we're going to rescale it. So we're going to say, we're going to evaluate this where capital omega is that, and that will basically scale it. And so it's a convenient way to go right from here through the sampling right to there. And so that's what we're going to do. We're going to sketch this, kind of sketch the signals bit by bit. So let's do that. We'll start off with this in mind. So this will be our continuous time signal. And basically applying this formula, this Fourier transform pair, we're going to say, we're going to be not real technical and say that the size of these delta functions is given by this, not the, this doesn't really mean a height because we all know that delta functions are infinite in height, but that's just reminding us that the size of these delta functions is pi. And our signal was what? 4,000 pi and plus 4,000 pi. So that gives us these two delta functions result in these two peaks or plots here. So the next step is sampling. So if we sample this, what happens? When we go back to our formula, we're going to scale it by 1 over t. So t was 1 over 6,000, so that's 6,000. And there's already a pi there, so right off the bat, we've got that down. What's the next step? Well, there's a summation from k negative infinity to infinity of all these shifted copies, and we're shifting it by omega s, which in our case was, what, 12,000 pi. So to make this easy, I just take each one of these delta functions and shift it by 12,000 pi individually. And of course, k can be 0, so there's a no shift version, right? So I'll do that first. But then there's the 12,000 pi shifted. So 4,000 plus 12,000 will be way out here. And this is the 16,000 pi. Of course, we can do the same thing with this guy. Let's see, I didn't draw the lines. So we bring this down, and that's minus 16,000. So I shifted him 12,000 this direction, but I also have to shift him 12,000 that direction. So 4,000 minus 12,000 puts him over here at minus 8,000 pi, right? 4 minus 12. So minus 8,000. Of course, we can do the same trick with this guy. Minus 12,000 this way resulted here, plus 12,000 would put another. And since this has a slash through it, I'm putting a slash there. 8,000 pi. And since this is a sampled signal, dot, 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 it goes on forever, dot, dot, dot. I only drew the first k equals 0, k equal plus 1, k equal minus 1, and it goes on and on. So we've got to this point. So given that, the next thing we want to do is find x e j omega. So what does the discrete time spectrum look like? Well, to do that, we're going to do the scaling, where omega equals capital omega times t. And remember, t is 1 over 6,000. So before we get started, we could look at each one of these positions in frequency, in capital omega, radian frequency, radians per second, and convert them into the, I guess just radians, which is the frequency variable of the discrete time. So let's do a few of those right off the bat. So minus 8,000 pi times 1 over 6,000. We got the thousands cancel, so that's what? Divide by 2, 4/3 pi. Minus. And what's minus 4,000? Let's move this up. Minus 4,000 pi times t, which is 1 over 6,000. Divide the thousands out, 4 over 6, that's the same as 2/3, so it's minus 2/3 pi. And that means what? Minus 16,000 pi times 1 over 6,000. It's just going to be double that, so that'd be minus 8/3 pi. Of course, the negative signs could be positive signs, so hopefully we have all our scaled values of the spectrum. So now we just have to apply this to our chart. So I'm going to hold that off to the side and say, okay, xj omega, and this is 9. And now what I'm going to do is replot this chart, but instead of using those values, I'm going to substitute minus 8,000 pi for minus 4/3 pi, minus 4,000 pi for minus 2/3 pi, and so on, which basically scales the spectrum and puts us into a discrete time spectrum. And I think I do. Don't I need the 1 over t? Is that right? No, I already did that for the sampling, so I don't think I have to scale the y-axis, because we're just scaling the x. The y-axis scaling came from the sampling itself. So we're back to 6,000 pi, and what this is 2/3 pi, and 8,000 was 4/3 pi. Yes.
I think I missed it. Like, why did we multiply it by 6,000 when it's multiplying by 1 over t?
So t is 1 over 6,000. So 1 over t is 6,000, right?
1 over t
Is that right? 1 over t.
Oh, we're multiplying by 1 over t. Oh, yeah, sorry.
Yeah.
Okay, I got it. Yeah.
Yeah, there's a lot of moving parts here. So we've got that, and what's this? This is just double that. So we're at, what, 4/3 pi? And out here was 8/3 pi. Dot, 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 because it's minus 2/3 pi. And I'll just do dot, dot, dot on that side. And I want to make sure this looks exactly the same, except for, so 16,000 converted to 8/3 pi, 4/3 pi was 8,000, 4,000 pi was 2/3 pi, and etc. So these plots are exactly the same. The only difference is now this is the frequency variable, little omega, and this is the discrete time spectrum. So that's how we normally get, or that's one way to go all the way through this. Now if we go back to the very beginning of the problem, I hope this sort of passes the smell test for you, because if we started with this signal and it was a cosine, we'd better see something that looks like 2 pi over 3 somewhere in the spectrum, right? Otherwise, something really has gone wrong, because that is the frequency of this signal, 2 pi over 3 in the discrete time. And so yes, 2 pi over 3 is exactly where it needs to be. So we've got our signal. Now the next thing we want to do is kind of put this off to the side. We know what the discrete time spectrum is. Let's go back to our sampled version, because today we're going to talk a little bit about this. Suppose you have this sampled signal and you want to go back and reconstruct it. And the reconstruction basically means I don't want any of this other stuff in the spectrum anymore. I want to get back to where I started, right? Because xc j omega is where I started, only had those components. I sampled it, I got these. So I need to get rid of these to get back. Excuse me. So to do that, we need some kind of low-pass reconstruction filter, which will basically, as a selective frequency filter, pass these components and attenuate the others. So that's where we're headed. So to do that, let's reconstruct with a low-pass filter, which I'm abbreviating LP, low-pass. Filter with the cutoff frequency equal to omega s over 2. And to start off, I'm just saying, trust me, omega s over 2 is the right answer. And then after we do this example, we're going to go back through and show you why a very popular choice and reasonable choice is omega s over 2. But first, let's just do the trust me, it'll work routine. So here's our continuous time reconstruction filter. It's not a sampled signal. This is a frequency spectrum of a frequency selective filter. And the height of this is t, which is 1 over 6,000. And the height of these reconstruction filters, or the magnitude, is always t, because as we did the sampling, it was 1 over t. So they'll cancel and you'll get back to whatever the innate magnitude of the spectrum was, which is what we want. So we're sitting here at omega s is 12,000 pi, because the sampling rate was 6,000 hertz. Divide by 2, that puts you at plus and minus 6,000 pi. So that's where that comes from. So what is the reconstructed signal? The reconstructed x is going to be a convolution in time or multiplication in frequency, right? So we take the sampled signal and multiply it. Where this was 4,000 pi minus 4,000 pi, and the height is back to 1. Or actually, it's back to pi, because that's where we started. Let's get back to square one, move everything on screen. So this is the reconstructed version, and it looks like the original version, the continuous time, minus 4,000 pi, plus 4,000 pi. We've got a size of pi for these two delta functions. We went through the sampling procedure, and we ended up with a bunch of shifted copies, which were here. So this 4,000 pi got copied everywhere. We then applied this reconstruction filter, which knocked out everything outside of 6,000 pi, and it brought us back down to this, plus and minus 4,000 pi. Why? Because if we go back to the sampled signal, what happened? We got cut off right here, right? So all these components were removed, everything outside, plus and minus 6,000 pi. And that's kind of a good segue because we want to dig into this reconstruction a little bit more and talk about how that's done and what these filters kind of look like. So with that, let's move on to that topic, reconstruction. So here we're given some discrete time signal. So that's our input. Before, some xc of t was our input. It was some continuous time signal, and then we did some kind of sampling. But now we're going to go in reverse. We're going to start in discrete time and convert it to a sampled signal in continuous time, and then filter it to remove all those samples that are all those spectral copies and reconstruct, just like we did in the simple example with the cosine. So if we start here, we end up going backwards from the, we'll call it a ideal discrete time to continuous time converter. So all these impulse trains have a size that are corresponding to xn, which is the input. So we'll end up with shifted copies of the spectrum. But we can filter it by a convolution in time with HR of t, where H is the impulse response, R means reconstruction, so it's the impulse response of a reconstruction filter. Sort of making this simple, we can say, well, it's just a block diagram in reverse of what we've been dealing with. Where here we convert a sequence, which is x of n, to an impulse train. Which is this step here. So that ended up giving us what? Xs of t. And then we're just going to apply our reconstruction filter, our HR of j omega. And it gets us out our reconstructed XR of t. So all these steps in a block diagram. And I'll move this up like that so you're still looking at it. It's very similar to what we did before, just in reverse. And there's a filtering step. Well, what is this HR of j omega? It's our reconstruction filter. It's typically a low-pass filter. And in our case right here, we're looking at the ideal case. So what is the ideal case?
Is there a difference between the lowercase HR and the uppercase HR?
This is a frequency spectrum, or a frequency response of the reconstruction filter. This small HR is an impulse response, so it's in the time. So this HR is time, this HR is frequency.
So it's after Z transfer?
You could say we're just looking at it in the frequency domain. So you could take, I mean, loosely speaking, you can kind of take an FFT of the impulse response if you were playing with it, but that's sort of loosely speaking. If you're being quick and dirty in MATLAB, which we will. basically the Fourier transform of the impulse response is the frequency response, which is this. And it's all in continuous time, hence the t there and the capital omega there. So as I said before, I just kind of threw out here, the ideal reconstruction has a frequency response like this, and didn't really say why that would be particularly desirable. Well, omega s over 2 was what was the assertion was a good one. And omega s is what? That's just 2 pi all over t, where t is the sampling period. But now we have this 1/2. So we've got that. Do the algebra, you end up with pi over t. So why is pi over t a good choice? For omega c. That's the question that we're going to answer now. Why does that make sense to have a cutoff of pi over t? So to do that, we'll just draw a little cartoon of a general signal. And we'll call that, we have some signal before us. It's plus and minus omega n. So there's our general signal. Now we're going to sample this signal. So what should we sample it at? Well, we could sample it at 100 times omega n. That would be just PG, right? But that seems like a lot of effort. How about we sample the slowest we possibly can? Because practically, the slower your A to D converters, what does that mean? It means less power. It means less data. It means you don't have as many data lines. It means you don't have as many powered data lines. It means a lot of things to reduce cost and reduce power. So it's a good trade if you can reduce, in general, all things considered, reduce the sample rates to the lowest possible. Well, based on our theory, we said, well, omega s equal to 2 times omega n is minimum. And for this case, it really is the fact. It really is minimum. So what are we going to do if we don't want aliasing? So if that's the case, and omega, let's see, I want to draw this on the same scale here. And we want omega s over 2, since that's the minimum. What does that mean? That means omega s over 2, divide both sides by 2, is really omega n. Right? So we're kind of making that trade right there. So hopefully that alerts you to, back here I asserted pi over t was good, which was omega s over 2. And crank, 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 that's pi over t. Well, omega s over 2 is pi over t, so really that's omega s over 2. And why do we choose that? Well, you have to satisfy Nyquist. So in general, that's a good thing to do. And if we make the copies, dot, 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 on both sides, that is omega n, but it's also omega s over 2. And this is omega s minus omega s, right? Because they're shifted copies every omega s. I guess in theory we should have put a 1 over t here, right? Because we're sampling. I think I misspoke over here. Let's go back to this chart. That needs to be t, right? Because in the ending, I want my reconstruction to cancel that out. So sorry about that. And I think that's it's not a 1 over t, it's a t. I have a tendency to do that from time to time. Let's try not to go there. So if we go ahead and sample at omega s, none of these overlap, and we don't end up with aliasing. Which is kind of restating the same thing as omega s was what, 2 pi over t. And if we let omega c, the cutoff, equal omega s over 2, that's just what, 2 pi over t times a half, which is pi over t. So really, all this is telling you is that you're satisfying Nyquist by choosing omega c pi over t. Now you could also say, well, wait a second. Why not make omega c in here? Why not make it cut off right here? Why not make it omega n over 2? And you could do that. You wouldn't have any aliasing. But you didn't maximize the available unaliased bandwidth either. And typically, maximizing your bandwidth is a good thing because it's more signals, more communication, more data, more everything. So in the general, what do you want to do? You want to satisfy Nyquist and translate and I guess communicate the maximum amount of bandwidth. Excuse me.
I have a question.
Yes.
Where draw the conclusion that omega c equals to omega s over half?
Let's see. Right. Omega c is the cutoff for the filter. So that's also another name for omega n, right?
Oh.
Because omega s is 2 times omega n.
Oh, I know that's.
So omega s over 2 is omega n. So our filter, kind of messing up my own drawing here, would take out just that.
Yeah.
And so we end up with basically harvesting all the available unaliased bandwidth. Typically you want to do that. Not always, but many times. All right, so now let's take a look at this filter in the time domain and kind of see what it's doing. So we said we have this, I think that's t, and we've got what, pi over t minus pi over t. And that's our reconstruction filter. Well, if we take the inverse kind of Fourier transform and go back, what do we end up with? This is a Fourier transform pair. With sine of pi over t and pi t over cap t. You may recognize this as like a sinc function that you've seen before. So if we march this sinc function back through, what does our final output look like? And it's basically kind of a signal decomposition. So if we got xr of t is, what did we say? It's the sampled version, which has all the shifted copies, times, or convolved, make sure that's a convolution with hr of t, which is the impulse response of that filter. Well, what is the impulse response of that filter? It's just a sinc function. So we can, in fact, carry this through. So what is the expression for the sampled one? This is our x of n's, t minus cap n t. So this is xs of t. We're convolving that with hr of t. Which is that expression. So somewhat complicated, but the good news, of course, is we're convolving with delta functions. So that'll make our lives easier. So we end up with the summation. We're going to convolve it with each one of these. So we end up with an infinite sum of x of n, but convolving this with that means that each t is replaced with t minus nt. So we end up with sine, and I think I want to write this pi t minus cap n t all over cap t. Nt all over cap t. So there we've got our infinite summation of sinc functions. Each sinc function has a weight, and that weight is the value of the signal, which is the discrete time value of the signal at index n. So that's sort of our big giant decomposition, sort of, is one way to look at it, as xr of t, which is what? That's our reconstructed continuous time signal. Is basically the discrete version, which acts as a weight to this infinite summation of, or an infinite number of sinc functions. So you've seen this kind of stuff before, like with a Fourier series, right? You can take a signal apart and put it into a bunch of complex exponentials, or like the Fourier transform, or a bunch of cosines like Fourier series, or in this case, how about that? A whole bunch of sinc functions. It can be done. So, a linear combination of sinc functions. Now, the sincs are a kind of, I like to think of them as basis functions. They're what we're using. They're sort of the Lego bricks that we're going to use to build back this xr of t. Now, just a point of note when you're trying to use this, because it can bite you. Sine of x over x is sinc of x in the mathematics world. Sine of pi x over pi x equals sinc x in the MATLAB world. So if you want, hilarity to ensue, ask a mathematician to write a sinc function in MATLAB if they haven't used it, and funny things may happen. But anyway, just a point to note there, because I've made that mistake before. This is just if you're talking to mathematicians, they're going to think sine x over x is sinc x, and so possibly I don't know if Mathematica, I haven't used it in a long time, or Maple, if there's a built-in sinc function that would operate this way, but I wouldn't be surprised if it does. But in MATLAB, I'll tell you, this is what happens. So for this class, if you want to use it, be aware. They already put the pi in there for you. So to kind of see what's going on in a little bit more detail, let's look at the behavior of our reconstructed signal at one particular point in time. So what we're going to do is go back to this ugly expression and say, I'm going to choose a particular time t. What happens over here? And what we're going to do is we're going to let t equal a certain time, and then we can break this summation up into two different cases to make it easy. Luckily, only two cases. So that's where we're headed. So kind of for the purposes of exploration, let's let t equal 3 times cap t. So this is just for exploration purposes. So let's go back and plug in for t 3 times capital T. And we end up with an infinite sum. And let's see, this is still n. All right, I want to make sure I don't throw that off. That's n. And we end up with what? Sine of pi times 3t minus nt all over cap t, and then the same thing in the denominator. 3t minus nt all over cap t. Okay, so we have this expression. Now this is an infinite summation over n, so we've got a lot of work to do here. It looks like if we're going to explore this, but let's break it up, as it turns out, into two cases. One where let's let n equal 3 and see what happens. And then if n equals anything else, you'll see something nice happens. It all goes to 0. But let's just sort of take it step by step. So I'm going to make a note here. This is an infinite sum over n. So we're going to let n equal 3 and see what happens. And I'm just going to say explore some, whatever you want to call this, the sinc function. That's kind of what we're doing. We're just going to see what happens. So inside this summation, what is this? Well, it's x of 3, right? That part's easy. And then we've got sine of pi, we've got 3t minus 3t all over t. And the whole thing is pi times 3t minus 3t all over t. So we're just letting n equal 3. So that's 3. This n is 3. Everything else is just drugged down here, and we're looking at one of these n's out of the plus and minus infinity just to see what happens. Well, you can see we've got a 0 in the numerator and denominator. So we're going to have to use some limit tricks to do this. And you've probably seen this before, L'Hopital's rule, right? So when you have this situation, you can basically see it's going to be the limit as n approaches 3t of sine ... over, I'm not going to write it all out because it's kind of doesn't really add much to the explanation. But what are we ending up with? We're ending up with something approaching 0 over 0. So this is going to be kind of sine of, this is approaching sine of 0 over 0.
Wait, is it the limit as n approaches 3 or 3t?
It should be approaching 3, because it can't be 3t, can it? Now I'm not sure that's very good math to have, because n is an index. But as the top and numerator and denominator approach 3, or as n approaches 3 and these approach 0, you've probably seen like the limit as, we'll just make up a dummy variable, as x approaches 0 of sine x over x. You know how to handle that, right? It's going to be, take the derivative. Derivative of sine is cosine, derivative of x is 1, so it's going to be 1. And in the same manner, we end up saying this limit, or this expression, is also 1. And so that was sort of a little bit slapdash mathematically, but when n equals 3, the answer, I guess, is just x3. That's the value of that whole sinc expression. Now that was just one value. What about the infinity of others? And so that's our next step, is to see what happens. So we've got one of them down, infinity to go. Let's go back and look inside the summation where, let's see, for all other n. Now remember, t still equals 3t. We didn't change that, but now we're looking at for all other n. So if that's the case, we have what? X of n is part of that summation. We've got sine of pi times 3 cap t, because That's where t is right now, minus nt, whole thing divided by cap t again. And it's pi 3t minus nt all over cap t. So what is this expression? And we're going to sum over an infinite number of these. Well, first thing to do is just simplify a bit. Let's divide out this cap t because it's a common term in both of them. So let's divide out by the cap t. This is just a note of what I'm doing next. So we end up with xn sine of what, pi times 3 minus n. All right, this is looking better. Divide by t, pi times 3 minus n. And n is being summed up from minus infinity to infinity. Well, if you look at this closely, you can say, well, this is good news, right? Because it doesn't matter what n is in terms of an integer. Because 3 minus an integer is going to be another integer, and pi times an integer, sine of pi times an integer is 0. And you could say, well, wait a second, what about when n equals 3? Well, we just did that case, right? Otherwise, we don't care. So this equals 0 for n not equal to 3. So let's put this together and kind of sum up what we just discovered or found here. The reconstructed signal xr of t, which is an infinite summation of those sinc functions, when t is evaluated at, we'll just say, some capital MT. So it's evaluated, this reconstructed signal is evaluated at some integer value, integer multiple of the sampling frequency. What are we getting back? We're getting back xm. In our case, we let m equal 3, and we went through the situation and found, oh, how about that? For one of those infinite number of n's, we've got that. And at 0 for n not equal to m. And hopefully this is unsurprising and a good thing, because one of the things you want to think is if you took a sequence and you sampled it at certain times, like every millisecond, the thing that would make no sense is if after you reconstructed it, the samples every millisecond were different than your original sampled signals. What kind of reconstruction would that be? That would be, I don't know, that would be very weird. If you can't get that right, then how can you trust anything, right? So that doesn't really make sense. So it has to be this way. And that's kind of what we went through, so you can see that even though this expression with all these infinite sinks may look, this may look intimidating, it really can't be. You have to get the same thing back. So xr of t equals xmt at sample time mt. It really has to. And if your reconstruction actually changed the samples at those times, that would sort of be a key that there's something very fishy about this reconstruction. So now I'd like to go to the, let's go to the computer here, because I made a little demo where we're going to take an arbitrary signal and we're going to filter it and create this, we're going to reconstruct it with an infinite number of sinc functions right here, like we talked about. And of course, I'm going to let t not just be mt, it can be over everything, because we want to see how well is it approximating the signal. Because I want you to be able to see that. And we're going to use not an infinite number, but 1, 2, 3, and let you see as we improve in what's happening to the signal. So let's go to the PC. All right, first off, the sinc interpolation filter. And the reason for bringing this up is one of the this is basically the HR of t that's being convolved. But I kind of scaled it this way so you can see at each sample frequency in time, what is it? It's a 0. And then everywhere else it has values. And that's very important because you only want the sink at that time to contribute to it, to the value at that time. Otherwise, you'll get something that's not the same as the original samples. And so that may seem a little wordy of an explanation, but let's keep going and hopefully it'll be clear or more clear. So, okay. I have this arbitrary continuous time signal, which is in dark blue, which I hope is visible. And we're going to try to reconstruct and get back to that signal as best we can. So that's the thing that we have. What would we do to get to sample it? That's these gray signals. So I used the stem command, which I think I asked you to do on your first homework to kind of get used to playing with the basic MATLAB visualization tools. So we sampled this blue signal and got this gray signal. So we have these samples. That's my discrete time signal. Now I went off at one particular time, mt, which was right here, and looked at the sinc function value. One single sinc. Well, good news. What happened? That is equal to the blue signal right there, which is equal to the gray signal. They're all the same. So this one sinc, and I think I pretended that, let's suppose we summed up that one sinc with nothing else. So as we go through this, I'm going to sum more and more sinks together and turn the trace black so you can kind of see how it lines up. Well, with one sinc, this is not a very good approximation to the blue signal, right? One sinc doesn't do it. We match at one place, right? And what's also the good news? At each value of the discrete time signal, the sinc goes to 0, which is great. That's what it's supposed to do because let's add 3 more sinc functions. So we have one here that's in purple. There's our red original, and here's our green. And notice that these are 0, where this is has the value of the signal, and so on and so forth. So when I sum these up, if I can, we get a little bit better. So hopefully you can kind of see where we're going with this. As we keep adding sinc functions at different times, we can keep improving it. And I think as we go, there's sum of 5, 9, and 17. I think I went to 25 because 25 made it look the best. So you can kind of see that if you really want to, you can take this signal and you can break it into a bunch of sinc functions and represent that signal as this basis. So each one of these sinc functions is kind of a Lego brick that you can use. And notice the time, notice they're also at a certain time. So you have to sum them up and they're all shifted to certain times. And they don't, and the nice thing is they don't interfere with one another and mess up the known locations of the signal. So hopefully that kind of shows you sort of what's happening under the hood with that summation of infinite sinks. So yeah, we got a good approximation there. So let's go back to desk camera and talk about our next subject, which is discrete time processing of a continuous time signal. And this is the case where you basically were going to implement something in analog, but nope, you can convert it to discrete time, process it in discrete time, and then send it back out in analog form. So we'll call it discrete time processing. Of continuous time signals. So this might be an application where you receive some signal that's analog, you do some sort of filtering to it, or other type of processing, and then you convert it back to analog and send it on its way, like some kind of repeater type processing. So the goal of this is to implement some kind of filter that you would normally do in analog. So we're calling it HEFF, which stands for effective. I think that's what the book uses. So we want to effectively cause this to happen. And for our example, we're going to say, well, I want to do a frequency selective filter. And 0 otherwise. So this is what I'd like to do if I had some analog filter, but I don't have it for whatever reason. So this is what we're shooting for. And we're going to implement this using HEJ omega, which is, a discrete time system. Using HE omega and discrete time system. So how does that work? Well, first of all, the input signal, we need to convert that to discrete time. So continuous time to discrete time converter. And so we'll get out x of n. Well, now that we have x of n, we can process it with HEJ omega. So this is our discrete time frequency or filter. And then finally, maybe we'll call that y of n because it's the output of some discrete time system. And then finally, running out of room here, we want to convert back from discrete time to continuous time and end up with, we'll call it y sub r for reconstruction of t. And each of these converter boxes has some sort of sampling frequency. First for going from continuous time to discrete time, and finally from going discrete time to continuous time and doing the reconstruction, which we just talked about. Now these values of t, or these sampling times, do not need to be the same in general. I think you have a homework problem where they're not the same. But for our simple example here, we're going to let them be the same. Now one note about this overall system is a linear time invariant system with some caveats. So if xc of t is band limited, which you'd expect that, and what, omega s, which equals what, 2 pi over t, had better be what, greater than or equal to 2 omega n. Or better way may just be saying sample fast enough not to have aliasing. So the first thing to do is to take a look at this HEJ omega and see how do we relate it back to the effective filter. So our favorite scaling function, small omega equals capital omega times t, means we can basically make this be a scaled version of the other filter. So that's going to be 1 if omega is less than or equal to omega c. I think we put 0 otherwise. And what's omega c? It's the cutoff times cap t. And this omega cap t was back from our effective filter. We want to implement this, but we want to do it in discrete time. So we've got our discrete time system. So let's just draw some pictures here. So let's first start off with let's not do that. Let's put it on this side. H effective. So this is what we're trying to achieve. Analog. And what we're going to do is do it digitally, or in discrete time. Omega c minus omega c. And dot 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 here because this is a discrete time spectrum, so it must always be periodic with period 2 pi. Okay, now there's two ways we can think about this problem to keep in mind, and you should always try to keep these in mind because they kind of help give you design trades about how you want to approach any particular problem. So let's think about how we'd approach this problem if we were trying to do this H effective. So I'm going to say there's probably more than two ways, but we'll break it down into two ways to think about it. So first way, omega c is fixed. Now this one is a little bit of a weird way, but it's almost like someone threw a digital filter at you and said, you must use this digital filter. Whatever you do, I don't care how you solve the problem, but you must use this digital filter. Well, that digital filter has a fixed omega c, and it was probably designed for something else. So to do that, let's think of it as, we know omega c is what? There's this relationship, right? And we can't change small omega c, that has been dictated. So we have to change cap t to get what we want, right? So let's think of an example. So let's say you're trying with an off-the-shelf digital filter and omega c is like pi over 6. And desired omega c is, let's say, 2 pi times 2000. So 2000 hertz or 4000 pi radians. That's what we want the cutoff to be. Right? So if that's the case, all you can do is affect your A to D frequency. So you have to solve for that. So you can go back to this expression and say, well, that's 2 pi times 2000 equals omega c over t. But omega c was given to me as pi over 6. I can't change it. So if we solve for t here, we get what? Pi over 6. Multiply this side times t, divide this side by 1 over, I'll call that 4000 pi. The pi's cancel, so we get 1 over 24,000. So f samp must be 24 kilohertz. So that's the way you'd approach it. You're forced to use that digital filter. It wasn't set up for what you wanted, but you have to use that. And the desired omega c, the cutoff frequency, was that. So you had choice on f samp. Of course, there's the other way, which is typically more common in my experience, is that t is fixed. And as I said earlier, there's a lot of reasons why t may be fixed, because that controls the number of samples, that controls the data rate through your system, and that can affect power, that can affect I/O, that can affect a lot of things. So the sizes of memories and FPGAs and other processing elements. So you have to be very careful that t is not so small that your system can't handle the data flow. So let's pretend that t is fixed. And as an example, let's say fsamp equals 1000 hertz. And in our case, our desired omega c is, let's say, 2 pi times 200. So what is that? An f cutoff of 200 hertz. That's what we're trying to do. So in our case, we want to find omega c. What's the cutoff of the digital filter? All right. Well, luckily, that's just that, which is capital omega c is what? 2 pi times 200. 200 hertz, and cap t is, where's fsamp? 1 over 1000. Right. So it's going to be pi, that's going to be what? 2 pi over 5? So that would be your cutoff for the digital filter, given fsamp and given your desired cutoff frequency and analog. So there's two different ways to think of it, at least, and those will kind of help you make your trades. Now I think this is a good place to stop. Next time we'll actually go through an example of processing the signal using that processing flow. And we'll stop here.
I'm not going. US cities are. US cities are. What's common? That's true. Yeah. I mean, there's no point. We don't have that on your size, but I don't think it has. Where is it? They say we can construct this. Why is it in the middle of the second?
Because when you do the shifted copies, and when you do the sampling, the samples are always at multiples of the sampling frequency. The copies of the spectrum are always at the sampling frequency. So I'll try to go back to the very beginning of this lecture where we're saying if you sample a signal, after it goes through the sampling process, what does it end up doing? It ends up taking the spectrum of XC and making copies of it. And the copies are spaced.
Like J.
They're spaced by omega s.
Oh, yes.
Yeah, J is just the way they like to do it in the book of showing that this is a complex argument. I'm not really sure why they do it that way, but I just sticking to it. Other books do it differently.
What is the signal that's being copied? It's just this half?
It's the whole thing. So you pick up that triangle and move it over, and just move it over.
So you're moving it over from this position?
Yeah.
This is the XS. That's what
Of course, yeah, because that's what started. That's what we started with. Because originally there was
the
nothing.
lines.
Yeah, originally there was nothing. It was continuous, and so there was nothing. You know, there was just this signal minus omega n plus omega n, and nothing else. Because this was XC of t, it was not sampled. That's the only content there is. And then once you sample it,
or do we sample it in the frequency?
or you sample it in time,
Okay.
but by sampling it in time, you create. You know, there's ambiguities, right? If you sample something in time, you don't know what happened between the samples. That ambiguity essentially creates all these copies in the frequency domain. So then you end up with XS, you know, J omega. So we started here, XC J omega, nothing. We sampled it. The ambiguities create these.
Okay.
So,
And
where
then
these are omega S, so those are
and these are separated by minus omega n to plus omega n.
right. And that's that difference. Because what we're saying is this is called the Nyquist rate, because as we reduce the sampling rate down, eventually these things will touch. And
That
so,
causes problems.
and
With
yeah,
aliasing.
that's the aliasing part. So if as long as they just touch, no problem. So then omega s could equal 2 omega n, no aliasing, everything's great.
That's why
According
we
to
want pi
Shannon,
over t.
and that's why you end up wanting omega s to be pi over t,
Got it.
or not. I guess
Omega s over 2 to be pi over t.
right,
Gotcha. And that's equal to.
or
this
not
over
omega s. Yeah, omega s over